Okay, here we go. So it's my pleasure to be here, and I also want like to congratulate Professor Yagi on receiving the Exner medal, of course. So I'm going to talk today about sustainable aviation fuel, which is something which gets more and more important in the decarbonization of the aviation industry. And it's all about the cooperation between my company, Proionic, which is located in Graz, in Austria, and my work as an affiliate senior scientist on the joint Bioenergy Institute located in Emeryville, which is driven by Lawrence Berkeley National Lab located in Berkeley. And so we are cooperating since 2016. Proionic is something which happened to me. I made an invention. I finished University of Vienna. I started with the first small startup company in a completely different field. I made an invention about ionic liquids, and I never planned even to found a company which produces chemicals. And I founded Proionic after I made an invention how to produce ionic liquids. I will show you later what ionic liquids are, cheaper and better and in higher quality. And so almost 20 years later, Proionic is one of the 3 largest producers of ionic liquids and one of the 3 leading developers of ionic liquids. So we are producing ionic liquids today in a volume of something like 200 tons per year, which is quite a lot in the world of ionic liquids. And we are now, in the next 2 to 3 years, we will be scaling up by a factor of 20. So we will be going in the multi-thousand ton range, which is a lot in the world of ionic liquids. And I never planned that, so it just happened. And that's something you should not underestimate your inventions. Yeah? It started with a simple, lousy experiment. And it got until where I am now. So we have a couple of partners in the company. There is not enough time to talk about everybody, but we are proud to have the Austrian Mint as one of our main shareholders, which is 100% daughter of the Austrian National Bank. And we are also proud to be within the Green Frontrunner program of the Austrian Research Promotion Agency, FFG. The Green Frontrunner program is a hidden champion funding program. And in the connection of this talk, one of our industrial partners is a company in Austria called Karasek, which is a global leader in industrial plant construction in the field of evaporation technologies. You will see this is going to be extremely important for the rest of the talk. Just a few words about the Joint Bioenergy Institute. It is a centralized institute which is a cooperation of a couple of scientific partners all around the US, America, and it's one of 4 bioenergy research centers, and they are developing the technology for biomass conversion to biofuels, to bioproducts, to bioplatform chemicals. They develop this technology to a point when they can hand it over to the industry. Yeah? And Proionic and JBEI are cooperating. And so what we are doing is we are combining our know-how in order to move forward with sustainable aviation fuels. So this visualization you see here is made by the US National Oceanic and Atmospheric Administration. And it's showing real flight tracking data on a certain day in 2018. So every yellow point moving here is an airplane, which was actually flying on this certain day in 2018. And you see it's like a swarm of bees. Actually, today we have something like 200,000 commercial flights per day worldwide, and it's increasing. In 2018, we had 4 billion passenger transports and 64 million cargo tons around the globe. 2.5% of man-made CO2 is coming from the aviation industry. which is consuming, by the way, around 300 million tons of jet fuel per year. And if you imagine that this is only 2.5%, you can imagine how much the rest must be if this is only 2.5%. I just made a calculation recently. Mankind consumes something like 3 times Lake Wörthersee, Austrians may know it, per year in terms of crude oil. And Lake Wörthersee is quite big. And so it's expected to increase several times until 2050. And the International Air Transport Association calls the only solution for this problem in order to decarbonize the aviation industry, drop in sustainable aviation fuels, the only way to move forward. So what are sustainable aviation technologies in general? I would say you can pretty much divide it in 2 parts. We have 2 feedstocks. One feedstock is electrons, and the other feedstock is biomass. If you have electrons coming from sustainable sources like windmills or photovoltaic cells, you can convert these electrons into hydrogen by water electrolysis and store the hydrogen in an airplane and directly use the hydrogen in a fuel cell or burn it in special gas turbines. You can, of course, also store the electrons directly. You can store the electrons directly in a battery and go to E-Aviation. Oh, what's happening now? Uh-oh. Seems like my talk has some problems. Does anybody know how to switch that? Because I'm not.
Das ist das Problem, das ist drin.
Because I see it now in your mode and you see it in my mode.
Da ist der Tanz wieder mal.
Anzeige tauschen. Okay. So I won't move with the mouse anymore. What you also can do, you can take the hydrogen produced by electricity and combine it with CO2, which comes from the atmosphere. You catch it from the atmosphere, or you catch it from an emittent, like a caloric power station, and you convert it with the hydrogen to syngas, which then is transformed by Fischer-Tropsch chemistry into hydrocarbons, for example. And then, of course, we have biomass in general. You can make sustainable aviation fuel from biomass. So I'm not going into the details of this table, but there are some important points on this table. So if we go to conventional jet fuel A, the energy density is around 11.9 kilowatt hours per kilogram. So the energy density, of course, is important. And if you go and look at E-Aviation, then you will see the energy density of a state-of-the-art lithium-ion battery is something like 250 watt-hours per kilogram. That's far away from anything realistic. For a transatlantic flight, you would have to have at least 1.5 kilowatt-hours per kilogram, and for regional flights, at least 0.6. So there is most probably no chance for E-Aviation that it's going to make it. If you look at hydrogen aviation, at first glance, the energy density of hydrogen with 33.6 kilowatt hours per kilogram seems to be fantastic. In reality, there's only one way to store hydrogen on an airplane, and that's cryogenic hydrogen, which has a lousy storage density in terms of volumetric energy density, which is only 2.4 kilowatt hours per liter. This means a 777 would have to carry 500 cubic meters of cryogenic hydrogen on board in order to make a transatlantic flight. So that's also not plausible. We have the e-fuels, I just told you. E-fuels are in principle a good idea, having high energy density. Problem is here, and they're also in demonstrating level already. Problem is here, the conversion of electrical energy into the e-fuels is very inefficient, so you lose a lot of energy on this pathway. They're very expensive, and you only can partially substitute the sustainable, the conventional jet fuel. You can only blend it in. So, and there are three other, and we are going to focus on this field now for the next slides, three other types of sustainable aviation fuels, as we call them, and they can be blended in as well, so you can't fully substitute the jet fuel by them. And there is one of them is commercialized. You can see it, for example, if you are at Frankfurt Airport, there is a big containment stating HEFA on it, sustainable aviation fuel. So HEFA is commercialized already with something like 1.5 tons, 1.5 million tons per year, and it's made by hydrogenation of fatty acid esters. Here the problem is low feedstock flexibility. You're depending on fatty feedstocks, and you run into a fuel versus feed problem, food problem, if you think about large scale. Yeah, there is not so much fat waste in the world to make that. Another option is taking lignocellulosic feedstock and gasify it and make Fischer-Tropsch chemistry. This is commercialized, almost commercialized. Here again, medium feedstock flexibility. And another one is alcohol to jet fuel. That means you produce alcohol, you dehydrate it, you isomerize it, and you hydrogenate it. And here the feedstock flexibility is also very, very low, runs also into a fuel versus food problem. And all of them are pretty expensive. That's also a big deal. But for all, the drop-in capability is the biggest problem. So you can't substitute the conventional fuel completely, and the feedstock flexibility. What is an ionic liquid? If you talk about sodium chloride as a salt, you know, has a fixed lattice, a very fixed structure, and has a high melting point. It consists only entirely of ions. The melting point is 800 degrees. If you melt sodium chloride, you get a liquid which consists entirely out of ions, but that's something we call a molten salt. If you combine the right ions, cations and anions, and that's something we know since 1914, you get a so-called ionic liquid. An ionic liquid is an organic molten salt in its liquid state having a melting point below 100 degrees C. That's the definition. And an ionic liquid could look like this. This is ethyl methyl imidazolium acetate. That's a gold standard for biomass applications. And that's a melt. That's not a solution. That's not an ionic solution. It's not a solution of ions in a solvent, but that's a melt which is liquid at room temperature. And in this melt, there is many different interactions between the ions. The predominant interactions, of course, are Coulomb forces and hydrogen bond interactions, and they are very interesting for applications in the biomass field. Probably it's worth mentioning that today, so it ramped up something like 2000. Today we have something like 20,000 patent families running and more than 100,000 scientific publications in the field. So it's quite large. So coming back to the topic, what about lignocellulosic feedstocks? Lignocellulose, of course, is the most abundant biomaterial we have on the planet, and it's consisting of three biopolymers, which is cellulose, cellulose filaments, which are wrapped with hemicellulose packages and which are glued together with lignin. So if you take lignocellulose, you have many different feedstocks. This can be waste feedstocks. In general, woody, grassy or herbaceous material. It can be municipal waste, forestry waste, whatever. And if you would like to work with this, you do have to disintegrate those polymers in order, or deconstruct them in order to convert them into sustainable aviation fuel. So what has been done is you take, You take an ionic liquid, you stir it with the lignocellulose feedstock, and this, let's say, disrupts the cell structure. In some cases, it dissolves the lignin, but it disrupts the cell structure. After that, you hydrolyze the sugars by enzymes, so you saccharify, you get monosugars, and then you feed the monosugars to certain bugs, which produce bioplatform chemicals, which produce biofuels, and also bioproducts. For example, you can produce isoprenol, which can be converted to isoprene, and you could make green rubber tires, for example, from this material. Interesting about this, alone in the United States, the availability of lignocellulosic waste materials and feedstocks is 1 billion tons per year, according to a very well-known publication. And this is also a program in the United States now running by the DOE. And that 1 billion tons of dry biomass per annum could be in theory converted to 200 million tons of sustainable aviation fuel. Remember, 300 million tons is the global consumption. So that's not only a few percent, that's a lot. Yeah. This is something I will skip because time is running away, but just a few words, one of the most interesting sustainable aviation fuels is called dimethyl cyclooctane, and that's something we're going to show in a few slides what it means in practice. There are other hydrocarbons which can be produced directly by organisms from the sugars. Not to forget, also not explaining this slide, would take too much time. Very interesting. We have the lignin as well. We have 10 to 30% of lignin. Lignin is a very interesting source for lots of bioplatform chemicals which could substitute platform chemicals used nowadays coming from fossil sources. So lignin itself is also something which is of high interest for the industry, and it would be a byproduct of this process. Now, what about the ionic liquids in detail? Ionic liquids are known since more than 15 years to be the most effective pretreatment medium for converting lignocellulosic biomass into sugars and feed them to bugs which produce, for example, sustainable aviation fuel. For all, it's important, if you pretreat biomass using ionic liquids, this is the best way to do it in terms of sugar yield, in terms, that's very important, of feedstock flexibility. So it works with almost any kind of lignocellulosic feedstocks, and in terms of robustness. This directly goes into your greenhouse gas emission reduction of your product and into the product price, of course, and also into your business concept. If you are dependent on a single feedstock, then everything gets pretty complicated if the price of your feedstock changes. If you are very independent on your feedstock, you are very flexible in reacting to changes in the market. So now we come to a signature property of ionic liquids. This is one of my first pictures I've been taking in terms of ionic liquids in my lab. And this was even before the proionic was founded. And it shows an ionic liquid which is called butyl methyl imidazolium tetrafluoroborate at a temperature of 170 degrees centigrades. It could have stand, by the way, more than 400 in terms of thermal decomposition, and at the pressure of 1 microbar. And this substance has a molar mass of about 170. So at this temperature and this pressure, organic substance with this molar mass should boil. Ionic liquids, one of the signature properties of ionic liquids is they virtually have no boiling point. They virtually have no vapor pressure. The vapor pressure is extremely low, and if you compare, for example, this ionic liquid with another polar substance, tetraethylene glycol, having a comparable molar mass, you see the vapor pressure is 9 orders of magnitudes lower than the one of tetraethylene glycol, and there is no boiling point. It doesn't boil. It can freeze, but it can't boil. So this, of course, is for many applications interesting. For example, if you think about gas absorption or cleaning or something like that, but it makes problems in the process for producing sustainable aviation fuel. So producing sustainable aviation fuel, the state of the art with normal ionic liquids is taking part in several steps. And the first step is the pretreatment, I already mentioned. And you cannot evaporate the ionic liquid out of the biomass slurry because it has no vapor pressure. So you have to wash it out. And that means you have to take loads of water, typically 30 times the mass of the biomass, to get out the lignin, some impurities. A waste biomass is never clean. There is lots of impurities inside. You have soluble lignin and insoluble lignin, and then you make the hydrolysis, you make the fermentation, you make the distillation of isoprenol, which is converted into sustainable aviation fuel. You have to separate solid and liquids, and at the end of the day, you have to go through ultrafiltration step, and then you have to remove all the water by evaporation. It's a complicated process, which is not very competitive. So in that case, the extremely low vapor pressure of ionic liquids is a problem, a big problem. So actually, we found it out based on an old paper from a person called Austrian and Gelb, very well-known scientist, which passed over a few years ago, sadly, in the field. And you can make distillable ionic liquids, which seems to be a contradiction to what I've said before. And that means, in the easiest way, what you do is you make an acid-base conjugate salt. Like you see here, you have a base and you have an acid, and you let react them, and you get, of course, neutralization energy. So it's an exothermic reaction, and then you get an ionic liquid. It's called a protic ionic liquid, and in some cases, it's a distillable ionic liquid. How does it work? You're heating the ionic liquid up, and let's say, you make a thermal decomposition, but in a controlled way. So the equilibrium shifts to the left side, that's all. And those substances are volatile. So you can distill off, de-educt, recondense them, they react back to the ionic liquid. So there are many different distillable ionic liquids with very different properties. Many properties can be derived from the delta pKa of the base and the acid. That includes also the thermal decomposition point, which we call a pseudo boiling point. I don't want to go into the details, but that way you can make a distillable ionic liquid. So this seems to be the goal, but it isn't. It's more complicated. If you go to a typical distillable ionic liquid like ethanol ammonium acetate, it has a boiling point of 210 degrees centigrades at 1 atmosphere. So you have now the biomass slurry from the pretreatment, where you would like to get rid of the ionic liquid. And to get rid of a substance with a boiling point of 210 degrees centigrades in a very viscous, heterogeneous slurry of biomass is something very difficult, especially as you have to get down to a very, very low, or let's say the other way around, you have to be very effective. You have to remove 99% or recover and recycle 99% of the ionic liquid in order to be competitive, but also because ionic liquids can have unwanted interactions with the enzyme or be toxic to the bugs you're feeding the sugars to. And so what we developed together with geek Karasek is a method which is applied already in the polymer industry in order to remove monomers from your polymers. What you see here is a device which is called a Visco-Film device. Other companies call it a film extruder. It looks like a pretty, let's say, bold machine, almost like a monster. So that's the inside rotor. And what you have is you produce a thin film of your biomass flowing down, and these blades here continuously disrupt the surface and create a new surface. So you have a thin film evaporation technology with continuous recreation of the surface, and you have very small, you have very short distance between the condenser and the evaporator, and if you do it that way, everything gets extremely efficient, and that's something you can see in this graph here. This is recovery rate versus time, done at exactly the same conditions in a conventional distillation device with blades inside, and in the lab version of this device here. And you see in a conventional device, so this is done with sorghum as biomass, you never reach more than 70% of recovery rate, but in such a device, you reach 99% plus in a few minutes. So this is patent pending, and it's scaled up now, and this seems to be a key for sustainable aviation fuel in general at, let's say, for the process we are developing together with the Joint Bioenergy Institute. And so this means this is the state-of-the-art process with non-distillable ionic liquids. And that's the new process, which looks pretty simple now, because you do not have to wash anymore. You can save one of the vessels, because now, I can't explain this now, it's too much details, but you can make it one pot. You get rid of the wastewater stream. You have no solid liquid separation, you have no ultrafiltration, and you have no recovery of water anymore. So the whole process is extremely easy now, and this also results in, on the right side, JBEI Sustainable Aviation Fuel has an energy density, by the way, which is 9% above the energy density of conventional jet fuel, which is a lot. 9% is quite a lot. It's in demonstrator level now. It's fully drop-in capable, so you can completely replace the jet fuel by JBEI Sustainable Aviation Fuel. There is no fuel versus food problem, because you can use lignocellulosic wastes. And of course, the feedstock flexibility is extremely high. And since JBEI was founded in 2007, they have a Techno-Economic, this is the second last slide, Techno-Economical expert group, Techno-Economical analysis expert group. They continuously predict the price level, because that's something which is important for the DOE, of course, yeah. And so the predictions today at the demonstrator level are between 1.0 and 1.6 times the price of conventional fuel. This is depending on how much side products you are able to sell. If you are able to sell side products coming from the lignin stream, then it will be 1.0, and if you are not able to sell it, it will be 1.6, something like that. But you see, this is by far the best available technology, to my belief, and also to the belief of JBEI, in terms of sustainable aviation fuels. And the last slide, what is currently going on? Right now, we do have test flights with the US Navy using drones. They are flying with 100% DMCO in the moment. And by the end of this year, spring next year latest, there will be business jet flights with this aviation fuel. And of course, we are nervous because you know, that's the day where the truth comes. Does it work? Does it really work over a long time? Using a conventional airplane with a conventional gas turbine, drop in the fuel completely. And you know, of course, there are lots of things have been tested, but you can get problems, for example, in stupid things like seals. Yeah? Some of the sustainable aviation fuels shrink seals, for example, and you can't replace the seals easily in an airplane. Yeah? And so we will see what's going to happen. And with this, I come to the last slide, which I always show to young people. If you would like to drive a company, you have to have passion, you have to find the right people, and you have to make profit in this order. Thank you very much for your attention.